yeah, buckle up indeed. So, so really, thanks for letting me have the opportunity to speak here. I should probably say, like, if you were unhappy with the number of assumptions from Andy's very nice talk yesterday, then maybe you'll be even more unhappy now. But I hope that even with all the assumptions, you'll still find the result interesting. So, so the subject of the talk is quantum field theory at finite temperature. And I'm mostly going to be thinking about scale-invariant quantum field theory at finite temperature. And I'm going to assume also Lorentz invariance. So I'm going to be thinking about z equals 1 critical points, you could say. And the really nice thing about this setup when you have a scale-invariant theory in flat space is that when you introduce some scale, like we learned yesterday in Andy's talk, the dependence of observables on this scale are heavily constrained by the fact that this is the only scale in the problem. And so if we think about computing some simple dimensionful observables, then the way that we account for the dimension must be in terms of this single scale. So here the scale is beta. Oops. Okay. Okay, the scale is beta. And that's the inverse temperature. But you could think about also just a Euclidean stat-mech model of infinite size with periodic boundary conditions along one cycle of some geometry, like a large slab with a finite direction of length beta. Okay, so so in the simplest cases where the correlation length becomes non-zero, or sorry, non-infinite, let's say, when we measure correlation functions along the infinite directions of this slab, at least the lore is that the leading effect of the finite temperature for a general manifold, so we could replace this R2 with some other manifold, and as long as this manifold is sufficiently flat, then the leading behavior should be governed by just the smallest scale in the problem, which is the inverse temperature. And the lore is that this is integrating, so to speak, integrating out some gap degrees of freedom that could lead to corrections to this effective action, gives you something that's local in the backgrounds, like the metric. But of course, you can also just directly compute the action, and then all of the, this would just be the leading contribution, and then there would be some subleading corrections that are, accounting for even gapless degrees of freedom or KK modes or whatever else happens. Okay, so now basically the question here is we can think about this problem as taking a non-trivial scale-invariant quantum field theory in 2+1 dimensions, let's say. So I'll always be working in 2+1 dimensions for the most part. And then we can just really think about trying to describe this 2+1 dimensional theory as a 1+1 dimensional theory, where we just treat this extra compactified dimension as essentially just setting some scale for a massive QFT in one dimension lower. And this may be not a very generic massive QFT, or even one that's close to having some Lagrangian description. It may have infinitely many fields and so on and so on. But nonetheless, we can just think about it as some two-dimensional quantum field theory, which is at least local still in the 2 dimensions. And this two-dimensional quantum field theory could have a mass gap. And as I mentioned, the mass gap should be measured in units of the temperature. So what I'll really refer to as the mass gap will be this dimensionless number, mu th. But I may interchange the dimensionful and the dimensionless quantity. Okay, so now, well, we already have 2 pieces of data now for this 1+1 dimensional QFT, which is the the free energy density. So if we think about the vacuum energy density. So if we think about, well, so this leading term here in the effective action can also be interpreted as fixing the vacuum energy density of the theory. And then we have this other dimensionless number, which is the thermal mass. And so, and in principle, like to study this theory in even more detail, we would want to specify more and more dimensionless numbers that that can eventually, like, fully fix the entire problem, or fix the entire theory. So, our remark is that in two-dimensional CFT, the vacuum energy density, if we reduce two-dimensional CFT on a circle, the free energy density is really, or vacuum energy density is really fixed by the central charge of the theory. So this is a really beautiful result of Carty that you basically just perform the flat space to cylinder map, and you can just compute quantities of the theory on an infinite cylinder, which is the infinite volume finite temperature limit of the theory. And in 2D, if you think about it, if I have a local 2D CFT, then the descendants of the identity are non-trivial states of this theory. And so no matter what theory we have, the minimum energy state on the cylinder, which is really what I would call the thermal mass, is has energy in units of temperature of 8 pi. So that's taking basically the TT bar primary operator. And so yeah, when I talk about thermal mass, I'll usually refer to the state that has zero momentum along the circle. So that will be what I'll call the thermal mass. Yes.
Sorry, just to make sure I understand this correctly. Mm-hmm. So SFT here is the scale-invariant field theory.
Oh yeah, sorry, yes.
And you are talking about describe. What does describe means? You are talking about some KK reduction of the competitive direction, or?
Yeah, I mean, so I want to. Well, what does it mean to describe a QFT? I don't even really know, but yeah. Mm-hmm.
Is this QFT supposed to be a local theory?
It should be local in the two infinite directions.
Why is it local?
I mean, well, I can just do, for instance, any local operator of the 2+1D theory. I can just take its Fourier modes around. So I mean, at least there's some set of local operators. Okay. This is an exact statement.
Yeah, I mean the operator, you could define local operator, but that doesn't mean that the Laplace.
But the stress tensor should also be a local operator of the 1+1D theory. I mean the Fourier modes of the stress tensor. So, and the zero mode is conserved also probably. So.
Why do you ever have to invoke this 1+1 dimensional theory? Why can't you just formulate the result?
Yeah, I think you could, but I think there's some. I mean, there's some quantities that have a natural interpretation in the 1+1D that I'll talk about. That, yeah.
So your statement about 2D, is that a digression to one lower dimension, or is it related to the? You start off with three-dimensional stuff. Are you just? Is this a digression of it, and then just problem one dimension lower? Or?
This line here.
Yeah.
Yeah, this is a digression to say like. That in 2D there's a theory independent bound on the thermal mass.
2D means 2D of, that's the higher dimensional theory.
2D is the higher dimensional theory, and now if I put it on a line at finite temperature, then it's yeah.
So why is like F greater than 0? And so like the free energy in 2D is minus C over 12.
Yeah, it's just a convention. So it's like C is positive, and F is I'm going to be taking as positive.
So C is positive, but F is negative.
No, like minus F is negative in my convention.
The answer to Ethan's question is just that the thermal mass gap is not zero, and that's why And you integrate out the stuff from the surface variable too.
Yeah, true. I mean, yeah, but I mean that's a very like that seems like a very like scary thing to do. So I don't know. I don't know. Okay, so okay, so like so somehow we want to study this problem from a non-perturbative point of view. There's different reasons for that. I mean, at a formal level, like there's a question of like what does it mean to put a CFT on some very non-trivial background. It's not clear to me that any that just for instance, the question of like if I just tell you what the local operators are, even if in principle that does specify everything about the theory, which is not even clear to me, the matter of at a non-perturbative level computing all of these other things seems like very, very tricky. And even the simple problem of computing correlation functions of the identity operator on an arbitrary manifold with arbitrary topology is like, that's an interesting observable already. And I cannot really see how this is really related to the properties of CFTs even that we know and love. So understanding, kind of trying to understand this question of how to compute things using sort of basic principles will be the motivating theme of the talk. And specifically, I'll be trying to study the thermal EFT, or not really the thermal EFT, but just the thermal QFT, using the Casimir energy of the 2+1D theory on T2. So yeah. Okay, so yeah, so thermal field theory is a very old subject, and there are many references here that I could add, especially from Monte Carlo, but I'm hoping to chat with some Monte Carlo people that I can get a more complete list of the current state of the art. But at least for perturbative field theory results, there are, a few that are interspersed throughout the literature. And some interesting features of these theories are, so we can look at things like massless scalar, massless Dirac fermion, ON model at large n at least, and even some more exotic things like Chern-Simons matter theories with scalars or fermions. And all of these theories have some various predictions for their quantities, but one interesting observation is, at least in these theories, the thermal masses are relatively like order 1, or even, okay, Dirac fermion maybe order 10, but it sort of depends on how you define thermal mass for Dirac fermion, because there's antiperiodic boundary conditions. But so yeah, so there's lots of results in the literature that, but I would say I would like more. And again with Monte Carlo, I think I just still haven't been able to parse through most of the literature.
What's C tilde?
Oh right, sorry. So C tilde is right. C tilde measures the gapless contribution. So if I dimensionally reduce the theory and then there's still a gapless mode surviving, scale invariance of this gapless mode basically fixes how it contributes to the free energy, and it contributes like a 1D CFT basically, 1+1D CFT. So you can measure that coefficient, for instance, in the massless free scalar.
So that is also why your thermal mass is 0?
Yes.
Okay.
Yes. But if you actually looked at like what's the lightest KK mode of this theory, then it would be probably 4 pi, at least in the n = 0 sector. Yeah.
But is this less than or equal to?
Yeah. Like so, there's in this scalar Chern-Simons matter theory, you can compute this as a function of the 't Hooft coupling. So there's a family of these theories, but yeah, the thermal mass just kind of like goes like whoop. I think it starts at 0 for, I think one limit is like free scalar and the other limit is like ON model or something like that. So yeah. Okay. So now, okay, so what I'm going to do is I'm going to really start with the background of a 3-torus. So I'm going to put my 2 plus 1D scale-invariant theory on a 3-torus. And oops. To start with, at least, we can think of, if I want to consider kind of quantizing this theory, we can basically think of the r direction as the imaginary time direction, and then the L and the beta directions as space directions. And so I'm going to want to be studying the energy of the theory on a two torus with side lengths L and beta. And if I were to construct the full partition function, it would have some, I'm going to assume that it would have some SL3Z invariance, although I'm not going to make a terribly non-trivial use of the full SL3Z, but I will sort of use it somewhere, although it won't be too interesting of an application of that. But so each energy level of this Hamiltonian that's on this 2 torus will be some function of some dimensionless function of the modular parameter of the torus by scale invariance, and then up to some dimensionful prefactor, which I choose just to make the dimensionless function have nice modular properties. So namely, under an S transformation, the energy level will be mapped to some other energy level with a potentially different momentum. And similarly, for a T transformation, there will be, again, some nice relation between energy levels of different momenta. You can drive this using the full SL3Z invariance of the partition function, but I won't. If you wanted to hear about that, you can ask me. But so well, it's an interesting question to ask about, like, aspects of the excited spectrum of the theory, and I have a whole story about that I could share with you if you'd like to hear about it. So just ask me again. But yeah, in this talk, I'm just going to really focus on the most basic question you can ask about the spectrum of this theory on a torus, which is just its Casimir energy, so the ground state. And so the ground state energy I'm going to also define by pulling out a minus sign from the previous expression, since the one thing you can prove by scale invariance is that the ground state energy must be negative, at least for tau real. Sorry, for tau purely imaginary, you can prove that. And so,
Is it hard to prove?
No. We can actually probably see it in a few slides that it's pretty obvious. Yeah.
So what's tau 1?
Yeah, sorry. So tau 1. Okay, so yeah, tau is tau 1 plus I tau 2. So tau 1 is the real part of tau. Yeah. Okay. So yeah, so we can understand a few aspects of this modular invariant Casimir energy, dimensionless Casimir energy. We can understand first the limit where the imaginary part of tau goes to infinity, and then the leading term to this contribution.
Right, I'm sorry, I'm a bit confused. So you had, can you write somewhere in the blackboard this half equations that you didn't write? Initially you had R L beta, then it became L beta tau 1, then tau. What is the relation with all this?
Sorry. So R
tau 2. So it's too many variables. Can you write on the blackboard what they all mean?
Okay. So yeah. So I have L by beta torus, right? And now, so this will be tau 1 beta, and now tau is equal to tau 1 plus I L over beta, and this is tau 2. Yeah?
So this is, and what is R?
So R will be the inverse temperature in the T3 partition.
But that's what you denoted by beta before. Yeah.
No, beta, I mean, doesn't matter. I mean, well, I want beta to, beta is the same beta as before. But now I'm doing I'm just looking at a different quantization. I want to keep beta to be the inverse temperature of the original 2 plus 1D theory. So this will always be my mass scale in in the entire talk. Yeah.
But you are restricting the two-torus to be square. There's no angle between the spatial direction and the time direction.
True. But you could consider to not have that.
And what is A?
A is the area. Area. It's L times B, beta. Mm-hmm.
So pure real tau for you is the square case.
Pure imaginary tau.
Oh, okay. So it's a standard definition.
Yeah.
Right.
Kappa. So kappa are the integer quantized. They're the integer. Yeah, they're just integer vectors corresponding to the quantized momenta around the cycles of the torus. Yeah. Okay. Any more questions about conception?
Sorry.
Yeah.
Kappa is corresponding to the r direction.
No. Kappa. So kappa is. So I have a two torus and I have two conserved momenta around each cycle, corresponding to translations around each cycle.
That's
so
n and kappa.
Kappa. Sorry, I mean n is just some other internal index of each energy level. So that's, and I'm going to assume that does not transform under a large diffeomorphism. You could also consider a situation if you have one-form symmetry, for suppose, where there are some internal degrees of freedom that mix with large diffeomorphisms. But I will assume that does not happen.
So your picture is in one space and the time direction?
Sorry, what?
Your picture there on the blackboard is in one space direction and the time direction?
No, these are these are two of the space directions.
Why is it called beta?
Because I always want beta to be, I'm studying a 2 + 1D theory at a finite temperature beta, and I'm thinking about this as a 1 + 1D theory with a mass scale beta. So I don't want beta to change. Beta will never change throughout the entire problem. So this is just along for the ride.
Wait, sorry, but you said so beta is a thermal circle. But
Beta is the original thermal circle.
But now you look at R as a thermal circle.
Right, but it could be also of infinite volume R, but it doesn't. Yeah, like it just depends on how you look at it. I have like a Euclidean large diffeomorphism invariant system, so I can just look at it as R taking like an infinite volume limit of a 1 + 1D system.
Why is it modular invariant? Modular covariant, this energy?
The energy levels are modular covariant, you could say. Yeah.
Why?
Yeah, so you have to argue it a little bit, but I think it's a little bit beyond the scope of the talk right now. I mean, yeah, I could derive view for you why this is true, but yeah.
So in the original 2 + 1D interpretation, that picture is the spatial coordinates.
In the original 2 + 1D, this would be like, well, there's a 2 + 1D interpretation where this is the spatial interpretation. So, yeah.
But really you want to say, I think, that in the original interpretation, since beta is always inverse temperature, beta is your Euclidean compact by time, right?
Yeah.
I thought that's how you want us to be thinking about it.
Yeah, but like from a quantum, like you could also take a 2 + 1D quantum mechanical system and then study it on a finite size, and like this would more naturally like describe like a 1 + 1D quantum mechanical system on it. You know, so yeah, it's kind of just terminology. So I don't know. I really struggle with this terminology, like what exactly to call things. So okay.
There was one equation in the previous slide that we didn't discuss.
Oh, which one? This one?
Yeah.
Oh yeah. Sorry. So yeah. Well, sorry. I think okay. So yeah. Good. So yeah. So one thing that you can derive is that if you assume that the leading contribution to the thermal effective action, you know, I'm assuming the theory is massive here at finite temperature, then you can match the dependence. You can match E of tau to this leading term, and then extract this leading term here, where the thermal 1-point coefficient or the vacuum energy density appears with some behavior of tau 2 that looks a bit funny with this convention, but it really corresponds to the cosmological constant or vacuum energy density of the 1+1D theory. But yeah, so sorry if this is now even more confusing, but so I'm going to actually, for technical reasons and I think conceptual reasons, I'm really going to try to think about the Casimir energy of the 1+1D theory. So the Casimir energy of the 1+1D theory I'm going to define as the ground state energy of the 1+1D theory, where I now put it on a circle of length L. So I take a 1+1D theory, which has a mass scale beta, and I put it on a circle of length L. And R will still be my infinite imaginary time. So I'm really taking the zero temperature limit and studying just the Casimir energy. And now I subtract an energy. So I subtract an energy corresponding to the infinite volume Casimir energy of the same 1+1D theory. And from this, I'll extract this quantity, which I'd call the Casimir energy. So I take the infinite volume, I take the finite volume limit and subtract the infinite volume result, basically. And
may I ask a silly question?
Yeah.
Will it be at any point relevant that we talk about 1+1 and not just 2D? Because it seems like you just work in Euclidean space-time. Why do you care about talking about imaginary time instead of just saying 2D? And that's it.
I could also do that, yeah. It's irrelevant, yeah. Yeah, and so then, so the Casimir energy then of this 1+1D theory, I can write in this way where I basically can divide out some fixed scale 1/beta, and then times the dimensionless function. And this dimensionless function will have the same L dependence as the Casimir energy does, except essentially up to this factor of 1/beta. And so, so this function C of tau will be like really the workhorse for most of the talk. And one interesting thing is, because of this flat geometry that we have, if we we can think about writing C of tau in terms of the full T3 partition function of the theory. And when we take the R goes to infinity limit, we essentially are taking this limit, we're taking the infinite volume limit of the Euclidean theory. Okay, let's just talk about, and there, we know what the leading behavior is. It's just this thing that's proportional to F. And so the remainder of this log of Z will have nice properties with respect to varying L.
Just to make sure I'm following, should the exponential be inside the log?
No. So I'm, but actually it should have a minus sign. So actually, sorry, that should have a minus sign. So I'm canceling off the free energy density in the infinite volume.
It's just that already has to the F inside. So once you took log, shouldn't you just subtract?
Sorry. Yes, it should be. It should be on the inside. Yes. Sorry. Okay. Good point. Yes. So yeah, it should have a minus sign and it should be inside. Good start. Okay. But just keeping you on your toes. Okay. Good. So. Yeah. Okay. But so basically, from this expression, if it were correct, we would be able to show that there are some constraints on this, some nice constraints on this function C of tau. So in particular, when...
So what does function C of tau call? It becomes dependence of the Casimir energy on tau?
Yeah. So and the dependence of the Casimir energy on tau is like how the 1+1D theory behaves when you put it on an infinite cylinder and you vary the short side of the, you vary the compactified side of the infinite cylinder.
These are most important equations so far, this constraint. They are totally not obvious. Why should this function be constrained in any way?
Mm-hmm. So the first row of constraints. Oh, actually, sorry. There's oh god, okay. So these constraints are true for n between 0 and 2.
Whatever n, why should they be true?
Right. So for n between 0 and 2, they're true because first of all, so this first constraint says that for real tau equal to 0, so I'm just varying the aspect ratio of the spatial torus, you could say. This first one says that C is positive, decreasing, and convex, and so it's positive because Z always has a contribution from the vacuum, so log of Z is always greater than 0. It's decreasing because I've factored out, again, sorry about this mistake, I factored out the ground state energy essentially, and so now all of the exponentials inside of Z are decaying with L. You could think of when you quantize it, when you think of this as like the infinite cylinder partition function. And then it's convex just because the second derivative really represents a standard deviation of the energy pre-unit length, and standard deviations are positive from like Jensen's inequality. So yeah, and then for the second row, well, n equals 0 is the same as before, and then well, actually, I probably would assume parity invariance so that the first derivative is automatically 0, and then the second derivative.
So there is a type of because for n equals 0 there seems to be a contradiction in the two.
Oh, sorry, true. Well, yeah, sorry, okay. Okay, many typos, geez. Sorry about that. Yes.
So it should be -1 to the n in both cases.
No, sorry. I mean, sorry. Only for n equals 0 is there a typo, but that's a redundant constraint.
Okay.
So I don't.
Okay,
yeah.
thanks.
So yeah. So the C of the second derivative of C of tau with respect to tau 1 will be actually negative. Basically, because I have a sum of decaying exponentials, and then I add a phase to them, so they should be sort of convex down or something. So, yeah. Okay, so C of tau in various limits encodes a lot of these quantities, or both of these quantities I've introduced that are important in describing the thermal properties of the 2+1D theory. So when tau becomes small, then by modular invariance of E, it fixes the behavior to be f over tau 2 squared. And when tau becomes large, based on the expression in terms of the partition function, we should expect that at large tau 2, it should decay with the thermal mass. And but in addition to these quantities, there are arbitrarily many more that come from the full functional dependence of the theory, and the rest of these ultimately I'll encode by considering an expansion of C of tau around the modular invariant point.
So Ryan, why do you only get inequalities instead of equalities? So in 2D you get equalities for modular invariance because you have C of -1 over tau equals Z of tau, and I thought you had a similar equation here.
Yeah, so there's an equation. Well, so I derived some inequalities that were really only related to this expression in terms of Z. E of tau is subject to some equality constraints from modular invariance, and those will be imposed soon. Yeah. Okay. So now I want to introduce some assumption on C of tau, and it's kind of so I think a useful mathematical concept here is the notion of infinite divisibility of random variables. So if I take a random variable with some probability distribution, then we call this random variable infinitely divisible if it can be written as a sum of independent identically distributed random variables. And by equality here, I mean equality of the distributions. So the total of these x tildes is distributed in exactly the same way as x is distributed. And so there's a certain special class of distributions for which a decomposition like this holds with varying probability distributions for the x tildes for any n, for any integer. And so I was kind of I was kind of thinking about the the thermodynamic or infinite volume limit in quantum field theory, and I kind of arrived at this guess, which is to say, are extensive quantities in a local quantum field theory infinitely divisible? And so concretely, I'm going to be asking if we stick a 1 + 1d QFT at finite temperature, which is considering this background R times S1, we can look at various thermodynamic observables, which are the simplest ones we can think of, like energy, momentum, entropy for energy. And all of these quantities are extensive in the infinite volume limit, and the densities I'm going to assume are well defined. And I'm actually going to assume that all these quantities are at least smooth functions of tau. This is not a totally generic thing, because there could be finite temperature phase transitions, for instance. But that will be one assumption.
There's some of densities, but the densities are not IID.
Well, yeah. So I don't know. Maybe they might not be. Yeah. Another thing is I have translation invariance. So so somehow, well, yeah. Let's try to get to it. So, so what I'm going to try to think about here is some quantity that I can define, which I think could have the interpretation that it represents the free energy contained in some region of width L, and L will be some arbitrary size of my region. And this free energy is defined by taking the thermodynamic limit of the difference of the free energy of a system of size R plus L, and then minus the free energy of the system with size R in the long direction. And then I'm going to take the long direction to infinity. Okay. So the proposal basically is that I can treat this FL, which is the free energy in a region of size L, as the free energy of some equilibrium system. And what this sort of amounts to saying for me, at least, is that I'm treating the rest of the system as like a thermal bath at the same temperature for this region of size L. And so quantitatively, what I'm going to assume that means is that if I exponentiate FL, then the partition function that I get from this will have the property that it is has an expansion as a Fourier Laplace transform of some non-negative spectral density. Okay, so I'm going to just give a name to these kinds of the theories where this is satisfied, which is that they're infinitely divisible.
So I'm a little bit confused about the logical path.
Mm-hmm.
So I assume that this infinite divisibility and probability theory has been studied.
Yeah.
So there's probably some result that if a variable is infinitely divisible, then something is true.
Yeah. So
then using that result, or yeah, you're cooking up something else.
Well, so like one thing is that, I mean, one result is that the characteristic function also has this, it has a factorization property. So so in QFT, the characteristic function is like.
I'm not really familiar with that result, as you can imagine. So
yeah.
What's going on here? Which theorem are you using?
Well, there's not really a theorem. It's just that. Sorry, there will sort of be a theorem, which is coming from this equation, which is. I mean, okay, I didn't want to get too into mathematics.
But how does this follow? For me, it's completely mystery. You wrote some equation, I don't understand where this follows.
Well, here I mean, it really is like, sorry, here I'm using physics to say that the free energy in the region of width L, is that, you know, that should capture fluctuations of energy in that region. And I'm assuming that the fluctuations of energy are governed by some canonical ensemble, or maybe grand canonical ensemble if I think of adding chemical potential for momentum. And then this is, and so now if there's some way to measure energy in this region, then what I'm saying by exponentiating f is that, well, I'm just getting the partition function of that region, where I've effectively integrated out the extensive part.
It's the next step that's the problem.
Which step? This one?
The part where you write the spectral representation of the partition function.
Yeah.
For me, that's the problem.
Right, but I guess that's where I'm saying that, like, this is the distribution. I mean, I'm using the equilibrium. You know, I'm assuming that.
Is this something trivial or non-trivial? The right-hand side of that equation.
I think it's non-trivial. Yeah, I'm not. I mean.
Yeah. So, but if it's non-trivial, can you motivate it? Like, for example, how would this? How would this fail? You know, what is the non-trivial part here? That this representation exists, that all phi's are non-negative. What is the non-trivial part?
I think I think it's non-trivial that the phi's are negative or non-negative. I mean, it's. Yeah, I mean, I'm assuming that f is smooth. So I'm assuming that the Casimir energy is smooth. So the existence of the inverse Laplace transform is probably okay. But now, to say that the phi is non-negative is, well, that's really like saying that, I mean, probably I can assign some probability distribution to fluctuations of energy in a region of width L. But now the question for phi to be non-negative would be saying that the distribution of the fluctuations is really canonical ensemble distribution, or Boltzmann weights.
Why do you need several phi n's? Because all terms for different n's look the same. Why can't you just sum them and define a single phi?
Because I want to capture the tau 1 dependence too. So. Oh, sorry, there's not an n. Jeez, oh my god.
There's no L either, so where does n and L?
Sorry, L.
Sorry,
Sorry, L is everywhere. So the distribution here will depend on L.
On small or on big L?
On little l. Sorry, I mean L. Big L is captured in tau 2.
Okay.
Yeah. Yeah.
So you want to say that this is like a sum of Boltzmann distributions?
Yeah, for each momentum sector, or for each KK sector.
I'm still confused by the integral over omega.
Because like omega is like the energy.
Well, you're saying I should think of phi as like the density of states.
Yeah, yeah.
Yes, so if we quantize in the beta direction, what can go wrong with this decomposition?
If I quantize.
Imagine quantizing the thermal decomposition, then it's a trace, and then I would expect to have sum over density to minus omega.
Well, right. So so when I send this little L to infinity, then that's like taking the original limit of large system size where R was going to infinity. Yes. And so then I should expect this decomposition eventually. when I take L to be sufficiently large. Because that's the actual density of states on the infinite cylinder. So now the question is, can I make L be small, of order beta, or even smaller, and still have a distribution, and still be able to get this positive or non-negative distribution?
Little L small or large L?
Little L.
Okay.
Yeah. So okay, so yeah, this is just a question. So we can ask if theories, if there are examples of theories that satisfy this constraint. And well, yeah, I mean, it's worth mentioning, if this could literally be true in some sense, where I could just literally write, sort of trace out the bulk and then write the result as an actual trace. And here, what I would really be asking for is, can I take some Hamiltonian, which is not even local in the L and the little l and the beta directions, with some choice of boundary conditions, and model the thermodynamics of the small region, which is fixed by this partition function. Okay, so that's that's a concrete question. And one thing is that this Hilbert space, the trace over the Hilbert space, should be really a continuum. There should be a continuum of states, because this is like this is like some fraction of the total density of states of the full system, which is continuous. And well, it's at least promising that there are examples of boundary conditions in two-dimensional CFT where the spectrum is known to be continuous with a non-negative density of states, where it's it's kind of interesting. Okay, but so anyway, the upshot of this assumption is that CF tau will inherit a similar expansion in terms of a non-negative spectral density, just by taking the L goes to 0 limit, where I essentially just take the Taylor expansion in L, and then keep only the regular piece after, or keep the only piece that survives after taking this difference of ZL minus 1. Okay, so this will be the really important constraint, and I'm kind of running out of time. But okay, but I should mention that this criterion is exactly true in a free scalar. So you can show that if I write CF tau for a free scalar, that based on just some simple property of the Laplace transform, or inverse Laplace transform of the Bessel function, that this function has an expansion in terms of Fourier modes with non-negative spectral densities for each Fourier mode. And of course, this well, okay, yeah, and this leading term is also an example of a term that I can write as one that has a positive inverse Laplace transform. Okay, so now, so for free scalar, I could think of it in a slightly more general way, which is that it's really like you could think of it as having this kind of expression, which is just the free energy density for just a non-interacting Bose gas, where here I subtract off the contribution from the gapless sector here. Well, there should be really a gapless sector, but this is just a more general thing, which is just if I have any non-interacting, any free energy corresponding to a non-interacting Bose gas, where I choose some spectrum of single particle energy levels and then integrate this log of the inverse Bose-Einstein distribution, that this will always have this infinite divisibility property. So now, okay, so now what I really kind of want to say to motivate this assumption is just that if I think of some massive bosonic QFT where you could roughly think about it as like something corresponding to single particle states and something corresponding to interactions, whether this if this is a decent model for the free energy per unit length of that theory, then the point is that the interacting part should not dominate the free part. at least if it's negative. But if it's positive, if it contributes something positive, then it's fine. As long as, again, this is like inverse Laplace transformable. Okay. Okay, but so you can also compute the free energy per unit length of the ON model at large n. And it's nice, so this is now a challenge, which is, can I try to probe whether this model is infinitely divisible in the sense that I described? And it's not manifestly infinitely divisible or not. And so it's kind of tricky to do computations here because I have to like numerically solve the gap equation and then plug it into the actual expression. And so everything is sort of has to be done numerically. But nonetheless, I can still try to check this. OK, so now what I want to do is study some systematic constraints on this function c of tau under the assumption that it has this positive inverse Laplace transform in each k sector.
Ask a question.
Yeah.
Initially, your partition function was the sum of exponentials. Then the c of tau is obtained from the partition function by some procedure. So, is it conceivable that all the properties that c of tau should have somehow reduced to that expression from the partition function?
Yeah.
But you don't know how to derive this property.
The positivity.
Yeah.
Yeah.
Can you explain when you say that it's not doesn't manifestly satisfy the divisibility property? But does that just mean that you can't look at it and tell, but it secretly does? Or does it mean it's actually a counterexample? Or does it mean you don't know?
No, it means I don't know. So, I mean, it's something I have to check.
But why can't you check?
Well, like, I mean, so there are, so what I'm going to tell you is basically that the space of these functions can be totally characterized. And so we can, and basically this, for each piece of data that enters into the definition of this function, which will be basically the Taylor coefficients of its series expansion around tau equals I, and the free energy, this coefficient f. Once I tell you those coefficients, each coefficient will live in a bounded region. And so now basically the goal is to show, do the Taylor coefficients of the ON model live in the region for each Taylor coefficient? Okay. So there's, so what I'm going to do basically, so the fact that I have this spectral representation means that when I do a Taylor expansion of c of tau, the Taylor coefficients will be related to some moment of a non-negative measure, and basically the thing that I'm going to use is the fact that the moments of a non-negative measure cannot just be anything, but they're constrained by various positivity conditions.
So Ryan, it's all very interesting, but it looks a little bit open-ended. Do you think in the remaining 5 minutes you'll be able to get to some?
Yeah, maybe. Yeah, so maybe I could just skip like how the bounds are derived because it's pretty standard in
I think
some
you should, should find some way out of it.
Yeah. So. So yeah, we can maybe skip the. Yeah. So, okay. Well, what I'm basically gonna tell you about are, I can write the Taylor coefficients of c of tau, which have a which are naturally constrained by this positivity constraint, in terms of the e of tau, which are constrained by modular invariance. And so, yeah, so the things I'm going to be really telling you about are bounds on derivatives of this e of tau, which is like the torus Casimir energy. And I'm going to be trying to explore the allowed region in the space of f and the derivatives of e of tau. Okay. So basically, there are some additional constraints that come from physical requirements. And in particular, we can say, like, if we assume there's an energy gap omega naught in the n equals 0 sector or any energy sector, sorry, any kk sector, then this kind of measure should be positive. Okay, so there's basically more positivity constraints you can write down, which is all great. But actually, okay, one thing I do want to say is that we can, we can ask about the dependence of the minimum energy or the minimum omega as a function of the kk momentum. And in principle, this could be unbounded. So for arbitrarily high k, I could have arbitrarily omega arbitrarily close to 0. There's nothing that obviously obstructs this, except that in the flat space limit, maybe we expect that omega should eventually be bounded by positivity of energy from like Lorentz invariance in flat space. But like for a free scalar or like OM model, it seems like omega is always bounded by n for all n. But so I just introduce a parameter here which measures the minimum energy as a function of n. Okay, so then there's some semi-infinite program you can write down, which is all nice. But in the end, you can put bounds on the Taylor coefficients of the torus Casimir energy. Yeah, and so we can plot the results of different bosonic CFTs, and so I choose the scalar, the OM model, and the Dirac fermion where I sum over spin structure. And you see that actually, so the Dirac fermion where I sum over spin structure is kind of a counterexample, but it also kind of doesn't really fit into the picture, into the assumptions that I made, because its vacuum energy is actually it transforms in a non-trivial representation of SL2Z, because it's not because the ground state of the antiperiodic sector could be mapped to, or of different sectors can be mapped to they transform non-trivially under the SL2Z. Okay, but so yeah, that's kind of this one is a bit anomalous, but I think it requires more thought. But the main ones I'm wanting to target are like the ON model and the scalar, and these all seem to be inside the bounds. So we can just compute these bounds for higher and higher derivatives, and we always seem to find that that everything is obeyed nicely. And now, but these bounds that I have before were like quite general, and so if I really want to test this assumption that the ON model is in the allowed region, I probably have to incorporate some more known data from the ON model. And so what I've done so far is to just input basically the f and the E0s and I import f and then the value of the torus Casimir energy at tau equals I. So I'm always going to be talking about things in terms of ratios of these quantities with respect to the Casimir energy at tau equals I. And then I also put in the second derivatives of the Casimir energy with respect to tau 1 and tau 2, which I can compute exactly, basically, up to some numerical precision. And then also the thermal mass is known exactly. And again, I expect gamma to be equal to 1. And now we just look and see that, like, I try to compute higher and higher derivatives. And indeed, as long as, so far, under the assumptions I made, this assumption that the ON model is infinitely divisible seems to very accurately predict, given these few list of input data, the actual values of the derivatives of the Casimir energy for higher and higher derivatives. So some of these are like quite tight, like the fourth derivative here and some of these other ones. And so, yeah, I mean, I think there's still a bit more work to be done, but I think it's at least promising that this seems to hold up so far at this level of the analysis. And then, well, one thing, okay, I should probably skip, but like it's kind of interesting to see actually that when you violate the expected limit of the gamma being, or sort of our energy being just exactly bounded by momentum at large momentum, the allowed region almost shrinks to nothing. So that's kind of cool. Yeah, sorry. Okay, so then basically there's more things you can compute, but okay, the namesake of the talk is that I have a bound on the thermal mass, and indeed, so you can study what's the minimum allowed energy in this expression that I have, and you could see that no matter how I tune f, it's bounded from above for any theory. Okay, so there's various future directions that I'll list on this slide that are interesting to think about, and I'll just end the talk now. Sorry for that.
What I don't understand is that, okay, we are used to modular bootstrap in 2 dimensions. Mm-hmm. Okay, there we know what you do, you write partition function, okay, you slice it and dice it and so on. But now, I didn't quite understand what you did exactly, but it's clear to me that you did something much more complicated, much more non-trivial than what we used to do. Can you explain like why simple tricks don't work, and why did you have to build all this beautiful theory of infinite visibility?
Yeah, so...
Did you try something simpler, or why simple things don't work?
Well, simple things don't work because, I mean, I think there's a few reasons. Like, I mean, well, if you don't assume this infinite divisibility, then you don't have any positivity. I mean, that's the most
important. You have positivity in the partition function.
Right. Okay. Good. Right. So what you'd like to do would be impose modular invariance of the full cylinder partition function. But well, yeah. But so I'm going to take the like S1 times S1 times R limit.
But why do you have to go to this limit? And 2D you don't go.
Because what I ultimately want to study is the spectrum of the infinite cylinder. Right. Well, that's what I want to study. So I want to see, can the gap on the infinite cylinder be large? And so, but the problem with that object, the partition function in the thermodynamic limit, is that it has this extensive divergence. And so this infinite divisibility is saying basically any way I cancel that extensive divergence by just like raising the partition function to some arbitrary dimensionless power that scales with the extensive divergence is like has this positivity property, which then allows me to get this, get the bounds.
But this energy levels on infinite cylinder, they don't depend on the size of the cylinder, right? So why, if your goal is to study the energy levels, for example, there were these numerical studies by Andreas and Casimir and so on, who studied torus partition function for using CFT, and they have some values for energy levels, which they determined numerically. Do we know if those values correspond to a modular invariant partition function?
I don't think we know.
Oh.
I mean, I think they should.
They should, yeah.
Yeah, but I don't think anyone's checked it yet. Okay. But yeah, that requires the full spectrum, I guess. Which is, I guess in the yeah, I mean, okay, so to study this limit, what you really need from ED or fuzzy sphere or something is really how the Casimir energy depends on the aspect ratio of the torus, at least. At the leading thing you would want would be that. And then, yeah, then we can use that to perhaps extract the thermal mass, for instance. Yeah.
I think I'm confused about something very simple. So if you start with the 3D ON model, let's say in the large N limit, and then you compactify it by temperature, you quote this thermal mass gap of 1 plus square root 5, etc. But I would naively expect that you then get the 2DO3 model, which undergoes dimensional transmutation, is asymptotically free, and has a much more subtle, exponentially small mass gap. So the theory is not scale invariant, but it's just asymptotically free. But what's wrong about that?
No, you don't get that because by the fact that you require that the 3D theory is conformal, means that when you dimensionally reduce it, you are not going to get a 2D theory in this regime where the coupling in the UV is very weak. You are just going to land in some other phase of the same theory which corresponds to a large coupling at the cutoff scale, and you're going to be directly massive. It's
okay.
Yeah.
It's in a large n limit. You're taking the gap to 0.
So this is only true of the leading
the
large n limit.
2D03 model is solved for all n by
yeah, but it's an exponential and minus n effect, right? Yeah.
So it's only the leading term in the 1 over n expansion.
No, the mass gap is e to the minus n.
Okay.
But the issue is not whether it's large n or small n. The issue is that when you dimensionally reduce, you don't get a UV complete theory in 2D. So you cannot use the intuition about some sigma models.
And that's because you're staying at the conformal fixed point. Is that the point?
Yes.
Yeah.
Questions?
Yeah. Sorry, I missed. So the infinite divisibility thing, what is the, could you say again what the assumption you want to make?
Yeah. Yeah, I think the part that's an assumption is that if I take the free energy that I get by taking the free energy density and then multiplying it by some arbitrary size to get the free energy in a region of that size, that when I exponentiate that quantity, it looks like a partition function in the canonical ensemble with positive density of states, non-negative, non-negative. Yeah, well, yeah, so Z sub L is...
It's defined by that relation. FL is defined on the previous slide,
right? Right. So, yeah, so actually, like, okay, maybe a question for Monte Carlo people is like, if I have a system that is large in one direction and small in the other two, what is the extra free energy that how do I compute the extra free energy that I get by increasing the size of the system by one layer?
No, but we are not now asking questions in this direction. That's for the
Okay. Okay, I would love to ask that question. So.
Because there's lunch also at stake.
Oh.
So any other questions to Ryan? Okay, thanks very much.
I have a question.
Okay.
What does the second bullet point mean?
Second bullet point. This one?
The
question?
I understand if you had a classical Slapmate problem, there are probability distributions, and then you ask exactly the same questions on the first time. But what do you mean in quantum theory?
The complaint is about the Q.
The Q, well, yeah, but I could think about a one-dimensional quantum mechanical system where I'm taking the infinite volume limit, and then I'm asking about the contribution to the free energy from a small region. Like, so...
The free energy isn't a random variable.
That's free energy. I mean, well, the energy is a random variable.
Okay.
So, like, but now free energy can help me understand the fluctuations of energy. So...
Is it just going to be like, if you have random variables which are not too strongly correlated, you're going to add them up and get a Gaussian distribution? Is that what you need?
Well, but it's the support of the random variables are all like positive. So, I mean, they're okay. It's yeah, it's not. Yeah, the distribution of the total energy is not Gaussian, I think. So.
Usually it's Gaussian, right?
Well, okay. It depends on what you mean, I guess. So.
Okay, Ryan, thanks for a tantalizing talk.